So, that so far we have looked into particle size distribution, right. Next thing is obviously we are interested in surface area, because we saw that in the first slide of this lecture that surface area influences your reactivity. If you are talking about dissolution for an example, that is dependent on your surface area, right, surface property. So, it is important to measure surface area, right. We will cover three commonly used techniques, right, in this lecture. So, we can use Blaine Air Permeability test. Most of you must be familiar with this, and we define Blaine fineness, right. When we have a cement, always it will have some Blaine fineness. So, Blaine Air Permeability test is used to determine that. Laser diffraction can also be used to determine the surface area, and also we will look into gas adsorption theory. Okay. Okay. So, what is Blaine permeability test? Basically, is derived from the resistance to flow of air through a porous bed of powder. So, you have a porous bed of powder, right, and we are basically measuring, right, what is the resistance to flow of air through it. Okay. So, the time needed for a fixed volume of air to pass through a well packed bed of powder of known dimension and porosity is determined. So, what are we measuring? We are measuring time. We are measuring time for a fixed volume of air, right, to pass through a well packed bed of powder, well packed bed of powder of known dimension. You know the dimensions and porosity. Okay. That is what we do in this. And surface area is determined considering this Cosenzi carbon theory that assumes again mono size and spherical shape of particles. See, you have to pay attention to these limitations, right. So, this is the assumption here, mono size, single size, spherical shape particles. And this air permeability apparatus is empirically calibrated. You have to calibrate this apparatus, and for that details you can refer to ASTM C204, which talks about how do you do calibration. That is what it looks like. This is a Blaine apparatus, right. So, you have a sample holder with prepared cement bed, right, a porosity around 0.05, you use roughly 3 gram of cement, right. Underneath that cement powder you have filter paper and perforated metal disc, that is here. And you have pressure control bulb here, right, that is what you use to control the pressure, and you have a manometer, right. So, again the principle of operation is that permeability of a bed of fine particles is proportional to the fineness of the particles. Okay. So, here what we are doing, the test is a measurement of the flow rate of air through a bed of cement powder. We are measuring the flow rate, right. How do we calculate? So, surface area of cement can be calculated using this relation, right, where S is surface area of your material, right, equals to SS is the surface area of reference material. So, pay attention, you need a reference material of known surface area, you have to calibrate it. So, you know that SS is the surface area of reference material, square root of T is the time flow of the material under test, you know. So, you are using your material, so how much time it takes, so you measure that. TS, you know the time of flow using reference material, so you have to calibrate your apparatus using reference material. Once you know these SS, you know already TS, once you know T, you can calculate surface area. And roughly the value you get, Blaine fineness for Portland cement ranges from 300 to 500 square meter per kg. Okay. That is the number you will find when you purchase cement, or if you ask for certificates, it will have this range. Obviously, it will vary depending on type of cement, but this is the common range. Okay. Okay. So, that was the Blaine air permeability test. We can also use laser diffraction, same thing what we discussed earlier, to determine the surface area. So, for spherical size of particles, SSA is specific surface area can be determined using this relation. So, here you know 6 over rho is density, and again what is Ni, Di, you know these are the size intervals, this is the average diameter in that size intervals, and small n is number of particles, right. So, you can use this to get the surface area, specific surface area, right. These all quantities you know already when you do your laser diffraction. So, unlike Blaine method, here LD method does not require any calibration. Here you do not need any calibration. No. And SSA's specific surface area calculated by laser diffraction are significantly lower than true value. True value because it does not take into account surface roughness. See, it is measuring the, it is based on the diameter, right, volume, right. So, surface roughness and porosity, because particles may have inherent porosity, and also there will be some roughness that will add to your surface area, which is not captured using LD. So, the values you get from laser diffraction is usually lower than true surface area. Okay.
Laser diffraction particle, the angle only we are calculating how much it is diffracted. So, based on this density and porosity it will vary.
So, we are calculating the volume. So, me theory we are calculating the volume of particle in laser diffraction. But in real life your particle will have surface roughness, porosity, so that will add to your surface area. So, the values you get from laser diffraction are lower. We only know, okay, here is a, so this is a size equivalent surface, but it might have some roughness that we do not know. I mean, it does not take into account. It may have inherent some porosity. We are only seeing is volume, right. So, these things will add, right, to your surface area, which is not captured using a laser diffraction, which is captured using your adsorption, gas adsorption theory, which we will discuss, because gas adsorption. So, these are the limitations, right, of earlier techniques. So, if you have a if you have high roughness, also if you have a porous particles, then your values from laser diffraction will be lower. Now, idea is how do you capture true surface area, right. Reality you have these particles which are irregular, which are porous, which are rough. So, for that we use adsorption, gas adsorption theory. What does it mean? First of all, what is the meaning of adsorption? It is not absorption, it is adsorption, right. So, it is a phenomenon in which molecules or ions of a solid, liquid or gas adhere to the surface of the atoms, ions or molecules adhere, right. The molecules that adhere or get adsorbed onto surface are called adsorbate, we call adsorbate. Like if you are using a gas molecule, it will be adsorbate, and the surface of the molecules on which they adhere is called adsorbent. So, you have a surface here and these are the gas molecules, right. What will happen in absorption? It will get absorbed also, right. See the difference, right. Here they are just in simpler word in adsorption, this is adsorption and this is absorption, right. So, in adsorption the molecules just sit on the surface of a substance, you can think of it, and we are talking about very weak bonds, not strong chemical bonds in case of absorption. Okay. So, the gas molecules are physically adsorbed onto the surface of a solid, physically adsorbed, not chemically. There are no chemical bonds. So, we are talking about van der Waals forces, right, between adsorbate gas molecule and solid surface. And usually adsorption measurements are carried out at cryogenic temperatures, typically liquid nitrogen 77 Kelvin, which corresponds to minus 196 degrees Celsius. Okay. These are the conditions. So, an adsorption, desorption isotherms are obtained by volumetric methods. So, we carry out this adsorption test and also desorption. Desorption is removing whatever is adsorbed, right, and we can get these isotherms. Isotherms is if you plot your volume, anyway we will come back to it, volume of adsorbed gas versus, let us say in this case, partial pressure, right. So, obviously it will increase as you are increasing the partial pressure. You can think of it as a relative humidity. All of you must be familiar with relative humidity, right. We have relative humidity, like if it is very dry, it is 20-30 degree means 20-30% relative humidity is very dry, less, very low, less humidity. If you go to 100% relative humidity means saturation, complete saturation, right. Similar concept, here we are talking about the pressure, right. And then you come, this is the adsorption. Similar thing, you can remove the adsorbed gas, you can get desorption branch, right. So these are the isotherms. We will come back to it, so you will know more. And we can, these are obtained by volumetric methods. Volumetric, we are calculating the volume of adsorbed gas, right. And the molar amount of adsorbed gas is plotted against the equilibrium gas pressure, that is what. So you are plotting the molar amount of adsorbed gas against the equilibrium partial gas pressure. So you can relate it to relative humidity concept in case of your concrete, like curing for an example, right. So now we are talking about these isotherms. This is a kind of a characteristic, right. What happens when you increase the partial pressure to saturated level, where your P over P0 is 1. How does a material respond? This is a specific characteristic. So IUPAC, according to IUPAC, adsorption isotherms are classified into 6 different types. So we have classification where we define there are 6 types of isotherms you can get. Okay. How do they look like? See the type 1, this is the type 1, look like reversible and concave to axis, right, concave to here, this is the x axis, P over P0 axis, right. This is a type 1. You can see that it increases, then reaches the plateau, no change. Type 2, see the difference, you have a concave, first you have a concave like type 1, then almost linear, right, then finally convex, right, concave, linear and convex. Type 3 is convex to P over P0 axis, okay. These are typical what we see, like these are the 6 types of isotherms, right, classified as per IUPAC. Type 4 is initial region is close to type 2, see this region is close to type 2, right, then it levels off at high pressures, levels off, right, here. What you see here is a hysteresis. Now this is adsorption, and what happens when you do desorption? So you will not come back on the same curve, that is why we call it hysteresis, okay. This signifies that it is a mesoporous material. Mesoporous material show this hysteresis. So basically this kind of isotherm will be applicable to cements, okay. Why we see this hysteresis? Because of capillary condensation. So what you are doing, you are filling pores, right, you are, as you increase the partial pressure, what you are doing, let us see, you have pores like this, right. Anyway, I have another slide on this. So these are the gas molecules, right, as you increase the partial pressure. So this is one case. So this suppose, no, let me do this, okay. So this is, we are starting from 0, right. So some gas molecules will get adsorbed. What will be the next stage? Then your whole, you will have a monolayer formation, right. What happens next? You may have couple of layers, right, then it will get filled as you increase the partial pressure, right. You can see the sequence, right. Anyway, there is a slide on that. Let us see here, right. So what happens? Stage 1 is isolated sites on the sample surface begin to adsorb gas molecules at low pressure, right. So not whole surface area is occupied. Stage 2, as gas pressure increases, coverage of adsorbed molecules increases to form a monolayer. Monolayer means one molecule thick layer. See, one molecule thick layer. We will come back to it. This we can use to determine the surface area. See, now suppose you have a monolayer formation and you know what is the volume of gas which was adsorbed, you can use that information to calculate the surface area. That is the principle here. But if you, this direction we are increasing the gas pressure, it is similar to increasing the relative humidity, if we can draw that analogy here. Right. So, stage 3 is further increasing gas pressure will cause beginning of multilayer coverage. Smaller pores in the samples will fill first, okay. Then finally, as you increase it, further increase will cause complete coverage of samples and fill all the pores, okay. This is the adsorption. Now, we can reduce the partial pressure also to get the desorption branch. That is what we see here, right. So, this hysteresis because it takes, when you come to desorption branch at the same level of, let us see, this is the partial pressure. Suppose, let us see, this is the P over P0, right. It takes more effort to remove it, that is what it says, right. So, when you are on adsorption branch, your volume adsorbed was this, right. So, when you are on desorption, you have this much volume, okay. This is signifies the capillary condensation basically, and you have to just remember this type 4 is for mesoporous materials, and it is applicable to materials like cements, right. Type 5 is initial convex. Now, see that it is initial convex, then levels off. This is initial convex, then levels off at high pressures. And type 6 is, this is stepwise. You see steps, that is what it is called, stepwise isotherms. So, these are the 6 different types of isotherms, obviously based on what kind of, like, applicable to different materials, right. Here I discuss this multilayer physisorption. We are using term physisorption, not chemisorption. Chemisorption will involve strong chemical bonds. Physisorption is weak physical bonds, van der Waals bonds. Okay. So, how do we calculate surface area? That is what we are interested in, right. So, commonly the most famous technique in gas absorption is BET theory, given by 3 scientists, Brunauer-Emmett-Teller. These are the names of 3 people. Combine it, BET, you might have heard, okay. So, BET theory, what is it? It is the extension of Langmuir theory. So, Langmuir theory basically the type 1 isotherm which you have can also be called as Langmuir isotherm. So, see, the initially Langmuir thought if you plot V versus P over P0, you have this kind of isotherm. But in real life you have different types of isotherms, right. Type 2 for an example. Type 1 it cannot explain what is happening in type 2, right. So, BET, these people came up with theory because Langmuir was relied on only monolayer formation, right, monolayer formation, then you have a saturation. But now they are trying to explain this behavior, why this is happening, okay, which is not type 1, you understand. So, in this they said, okay, so in this they say like the point B, right, where you see the change in slope, this point B, the point most likely to correspond to monolayer completion. They say like, here is the point where your monolayer completes, monolayer we are talking about, layer of 1 molecule thick, monolayer completes. How did they? So, they did, after calculating the hypothetical surface areas, okay, what they did, they took these points B, C, D, okay, A, B, C, D, then they calculated the surface areas, okay, and the closest agreement between various values of surface area was found by the uptakes at point B. So, you can calculate surface areas based on these, right, based on this volume, right, but the closest agreement they found was for P, okay. So, what are the assumptions here? The adsorption energy is constant during the formation of the first layer, okay. the adsorption energy does not change when you are forming the first layer. Only the uppermost molecules of multi-layered adsorbate are in dynamic equilibrium with vapor. So, you have a suppose multi-layer formation, right. The uppermost molecules of a multi-layered adsorbate are in the dynamic equilibrium with the vapor, they are in equilibrium. Heats of adsorption of the second and higher levels equal to the heat of condensation. Molecule covered by another molecule cannot evaporate. So, if you have another molecule covered, it cannot evaporate. At saturation, the number of layers become infinite. When you have full saturation, then number of layers will be infinite. And no lateral interaction between adsorbed molecules. There is no lateral, like you will have, you have a surface. If you see plan, you will have these molecules. So, there is no lateral interaction. Okay. These are the assumptions of this theory. So, finally, they were able to come up, we are not going in detail, they were able to relate what you see Va over Vm. Va is the amount of gas adsorbed at pressure P. Vm is amount of gas needed to cover the surface with a monolayer. Va over Vm could be related to this partial pressure P over P0. P over P0 will range, right, 0 to 1. 1 is fully saturated. So, this relationship could explain the trend. So, if you plot it based on C value, right, C is the constant here, you get this kind of isotherms. So, they were able to explain isotherms like type 2, right. So, that is why it is called extension of Langmuir theory, right. Langmuir would be like, it will be like something here, right, but could not explain these isotherms which we see. So, anyway, they came up with this. Now, the question is, okay, another thing is depending on the constant, right, C, you see here C is the constant, you can get different shapes, right. Okay. So, now that equation can be written in linear form also. This is not linear. Same thing you can write in linear form as this. So, P over Va times P0 minus P equals 1 over Vm, all everything you know. P is the pressure, at Va is the amount of gas adsorbed at pressure P, right. P0 is the saturation pressure of gas, right. P is the pressure of gas in equilibrium with sample, right. All these things are you know. So, we can now suppose this is y, this is x, right. We can write the same equation in this form. Now, what we see, if you say okay, this is your, this is you are varying this partial pressure, right. If you plot y over x, y against x, this is like a straight line. So, y is suppose P over Va P0 minus P, you will get a straight line, clear. This is x, this is x, this is y. So, what does it tell you? Then you can instantly see your slope is C1 minus VMC, right, and your intercept is this. So, this is your M, this is your C, clear. Okay, let us see, not confuse it, say C1, okay. Intercept, let us see I for example. And this is slope S. Okay, slope and intercept. So, basically you can get constant C, C minus 1 is nothing but ratio of slope and intercept, right. You got this plot, now you measure the slope, you measure the intercept, divide it, you will get the constant C, right. Also the Vm, we are interested in what is the amount of gas needed to cover the surface with a monolayer, okay. So, Vm can be calculated as 1 over slope plus intercept, it is simple, right. So, when you do slope plus intercept, what will be slope? So, you know already slope and intercept, right. Slope plus intercept is equal to C over Vm C. So, Vm is 1 over slope plus intercept, right. So, if you know slope and intercept, you can calculate Vm and C. Okay. We will stop here, we will start tomorrow, and we will see how we can calculate the surface area, and we will also look into applications of BET in cement based materials.